In this video, we'll look at the formation of ions and subsequently ionic bonding. We know that ions occur due to the gain or loss of electrons. In this example, the hydrogen atom loses its outer shell valence electron and it becomes the hydronium or the positive hydrogen cation. In this example, the fluorine gaining an electron becomes a negative ion. Well, why does this occur? Let's make use of our periodic table and start to look at some of the trends and some of the other information that we can gain from our periodic table. We'll specifically use this one that can be found on the Science Geek website, and it's great because it's got what are referred to as oxidation states labeled on the periodic table. If we look at this staircase, it helps us differentiate between the large group on the left, which are referred to as the metals, and those on the right called the nonmetals. The area in green is referred to as metalloids. Hydrogen tends to act as both a metal and a nonmetal. That is, its behavior, its gain or loss of electrons, puts it in both categories. The gain or loss of electrons is due to something called electronegativity. It's an attraction or a measurement of the attractive force that something has on electrons. This could be an atom's attraction or a group of atoms and their attraction for electrons. Something with a greater electronegativity is going to attract electrons from something with a lower or lesser electronegativity. If we look at the general trend on the periodic table, we see that as we move from left to right on the periodic table, we see an increasing electronegativity. We also have an increasing electronegativity near the top of the periodic table. For our purposes, that main trend from left to right is what we really are going to focus on with this first step of ionic bonding. Helium ultimately has the greatest electronegativity, and francium down in the bottom left would therefore have the lowest electronegativity. But what this means for metals and nonmetals is that metals have lower electronegativity than nonmetals do, which means nonmetals will tend to attract the electrons of metals. This makes a lot of sense when we go back and look at that initial example of our hydrogen atom, which lost its electron to fluorine because fluorine has a greater electronegativity. What ultimately occurred was we had the formation of that hydrogen positive ion and we had that fluorine negative ion. We know that opposites attract, therefore the positive ion will be attracted to the negative ion. This creates the compound referred to as, or represented as HF, or referred to as hydrogen fluoride. Going back to our periodic table, this area up in the legend shows us something called our oxidation states. And all an oxidation state is a fancy name for the possible charges that that particular atom can have. Depending on its electron configuration, that electron, it can gain or lose multiple electrons. In the case of mercury here, we see that it could end up forming an ion with a positive 1 charge or a positive 2. So if it was to lose 1 electron, it would be plus 1. If it lost 2 electrons, it would be plus 2. And that was true of that's true of many atoms on the periodic table. Those in group 1, not the case. They only lose 1 electron in their outer valence shell, therefore have a charge of plus 1. Again, the exception to that being hydrogen. We see those in the second group will lose both of their electrons from their outer valence shell and form ions that have a charge of positive 2. We see this trend continue until we hit this area called the transition metals. And you'll notice in the transition metals, many of these have 2, 3, 4 possible charges that they might form. And again, this has to do with the electron configuration of that particular atom. This is something that we get into in our senior chemistry classes when we really start to understand the location and the energies associated with various electrons. Moving over to the halogens, Again, we get into a more simple trend, though this periodic table does show all the possible valences. In the case of binary compounds, we are looking at these having a charge of -1, -2, -3 in this column here.